Welcome to this video where we take a look at differentiation from first principles. I hope that this video will help in particular first year A-level maths students to better understand this concept. So differentiation from first principles is a technique for differentiating functions, starting with the limit definition of derivative. For a function f of x, f primed x is defined to be f primed x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, where delta x represents some variable which takes non-zero values but which approaches 0. Sometimes h or just delta will be used instead of delta x, but this doesn't change the meaning of the definition. F primed x is called the derivative of f with respect to x and is sometimes written d by dx of f of x. Sometimes this might be written in slightly different forms. For example, you may see an unsimplified expression, x plus delta x minus x, in the denominator. But of course, x plus delta x minus x just simplifies to delta x. And you may also sometimes see other slightly different forms, but they all pretty much amount to the same thing, at least as far as we're concerned here. Anyway, I'm not going to get bogged down with technicalities at this stage. If we have y equals f of x, then we also write dy by dx equals f primed x. In other words, dy by dx equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And dy by dx is called the derivative of y with respect to x. Although dy by dx looks like a fraction with numerator dy and denominator dx, it's not a fraction. Dy by dx is a single symbol. The notation is not random. The notation is, I suppose, intended to indicate that dy by dx is in some ways comparable to the idea of gradient of a line. The gradient of a line is computed using the formula delta y over delta x, where delta y and delta x are in fact numbers, and therefore delta y over delta x is a kind of fraction. But there will be occasions where dy by dx will be formally treated like a fraction, and the dy and the dx will appear to be separated. This kind of formal manipulation can be made, but only if done with very great care. And you may see this happen, for example, when you come to integration by substitution. And I'll say more about this integration by substitution in the video that I make for that particular topic, if and when I get around to making it. F primed x is sometimes called the gradient function of the function f of x, since f primed x can be used to tell us what the gradient of the function is at the point with coordinates x f of x. The gradient function will also tell us the gradient of the tangent line to the curve at the point with coordinates x f of x. And I'll explain more about this in the extra stuff section to this video. So let's jump into some problems. As I go through these problems, I'll try to explain what I'm doing as I go through, and I may not follow set methods as I work through the problems. I just solve in whichever way comes to mind. So let's go. By using differentiation from first principles, prove that d by dx of k equals 0, where k is a constant. So let f of x equal k. Then by definition, d by dx of f of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And so, since f of x equals k for any value of x, and that includes x plus delta x, then d by dx of k is equal to the limit as delta x approaches 0 of k minus k over delta x. And of course the numerator is just equal to 0, so we get the limit as delta x approaches 0 of 0 over delta x. And since delta x is a non-zero number, then 0 over delta x is equal to 0, which means that the limit as delta x approaches 0 of 0 is equal to 0. And of course, this corresponds to exactly what we expect. When we view the derivative of a function as the gradient function, a function which numerically describes the gradient of the function at a given point, then we see that this makes perfect sense. The line y equals k is a horizontal line parallel to the x-axis, and so its gradient is equal to 0. Use differentiation from first principles to determine the gradient of the curve with equation y equals x squared minus x plus 2 at the point when x equals minus 3. So we can go about this in a couple of different ways. The first is to find the gradient function, of course using differentiation from first principles. The gradient function of x squared minus x plus 2 and then substitute the value x equals minus 3 into this to find the gradient. Secondly, you can just go straight in to find the gradient at the point of interest without bothering to find the gradient function first. Neither of these approaches is necessarily better than the other. I personally would be happy to go for either approach, and it depends on what kind of mood I'm in. Today, I feel like going for the second approach, so calculating the limit of minus 3 plus delta x squared minus 3 plus delta x plus 2 minus 3 squared minus 3 plus 2 all over delta x, and expanding out the brackets gives the limit as delta x approaches 0 of 9 minus 6 delta x plus delta x squared plus 3 minus delta x plus 2 minus 9 plus 3 plus 2 all over delta x. And simplifying the numerator by cancelling anything that can be cancelled gives the limit as delta x approaches 0 of minus 7 delta x plus delta x squared over delta x. And now divide each term in the numerator by delta x to give the limit as delta x approaches 0 of minus 7 plus delta x, which of course is equal to minus 7. And therefore the gradient of y equals x squared minus x plus 2 at the point when x equals minus 3 is equal to minus 7. So now let's have a look at some problems that are a bit more complicated. There's no suggestion that the problems which follow will be anything like you will get on an A-level maths exam. I don't really care whether they are or are not A-level style exam problems. They're simply problems that involve differentiation from first principles. If it puts you off that they may not be A-level exam style, then skip over this part of the video. But I'll try to explain my solutions to these problems as best I can. As always, there is no reason to believe that the way that I solve these problems is the way of solving the problems. The solutions that I present are just the solutions that I came up with and which seem to work. So let's have a look at differentiating 1 over x cubed with respect to x from first principles. So let's set f of x equal to 1 over x cubed. And then of course we start from the limit definition of derivative as shown on the screen now. And so d by dx of 1 over x cubed is equal to the limit as delta x approaches 0 of 1 over x plus delta x cubed minus 1 over x cubed all over delta x. And this is equal to the limit as delta x approaches 0 of x cubed minus x plus delta x cubed over x cubed times x plus delta x cubed times delta x. And now use whichever is your favourite method of expanding brackets to expand out the brackets in the numerator, but not in the denominator. Leave the denominator alone. And this gives the limit as delta x approaches 0 of x cubed minus, and then in brackets, x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed over x cubed x plus delta x cubed times delta x. And cancelling any terms in the numerator which can be cancelled gives the expression as shown on the screen now. And now dividing each term in the numerator by delta x gives the limit as delta x approaches 0 of minus 3x squared plus 3x delta x plus delta x squared over x cubed times x plus delta x cubed, which of course is equal to minus 3x squared over x to the power of 6. And using laws of indices, this gives the result minus 3x to the power of minus 4. In other words, d by dx of 1 over x cubed is equal to minus 3 over x to the power of 4. Given that y equals x to the power of 3 halves, find dy by dx using differentiation from first principles. So just a warning, this is not as straightforward as some of the previous examples. I would not expect this to appear on an A-level maths exam, but this level of difficulty may be possible on a step exam. So let's start with the limit definition of dy by dx to get dy by dx equals the limit as delta x approaches 0 of x plus delta x to the power of 3 halves minus x to the power of 3 halves over x plus delta x minus x. And now we can use the identity a cubed minus b cubed equals a minus b times a squared plus ab plus b squared to rewrite the numerator to get the expression shown on the screen now, or even better, the expression as shown on the screen now. And now use the identity a minus b over a squared minus b squared equals 1 over a plus b to rewrite the square root of x plus delta x minus the square root of x over x plus delta x minus x as 1 over the square root of x plus delta x plus the square root of x, giving the expression as shown on the screen now. And now taking the limit as delta x approaches 0 gives x plus the square root of x times the square root of x plus x over the square root of x plus the square root of x, which of course is equal to 3x over 2 times the square root of x. This of course is equal to 3 halves times the square root of x, and so therefore dy by dx is equal to 3 halves times the square root of x. Differentiation from first principles is not some weird type of differentiation. I've often had A-level maths students of mine refer to application of the rule d by dx of k times x to the power of n equals kn x to the power of n minus 1 as normal differentiation in inverted commas, as if differentiation from first principles or differentiation using other techniques such as the product rule or quotient rule or the differentiation of other functions is somehow some sort of weird or unusual type of differentiation. The limit definition of derivative is arguably what it means for a function to be differentiable or capable of being differentiated. Of all of the techniques that can be used to differentiate functions, differentiating directly from the limit definition, that is from first principles, would be the most desirable and most elementary method, though it's not necessarily always practically possible to do this, and sometimes more sophisticated techniques may need to be used. Our interpretation of the derivative as the gradient of a tangent line is a very useful interpretation, but there may be times where this interpretation breaks down, and we really have to work with the symbols directly rather than trying to interpret geometrically. For first year A-level mathematics, you'll be limited to using differentiation from first principles for small integer exponents of x or some other variable. In the second year, you will use differentiation from first principles to obtain derivatives for some trigonometric functions. However, differentiation can be used to obtain derivatives for a wide range of different functions in theory. It's just that the arguments sometimes have to become more subtle. There may often be more efficient but less direct and less elementary ways of obtaining derivatives. The limit definition of derivative can also be used to prove general results for differentiation, such as the sum rule, the product rule, and so on. As I'll show in another of my videos on this channel, the rule d by dx of kx to the power of n is equal to kn x to the power of n minus 1, where n is an integer. This rule can be proved using differentiation from first principles and a few other first-year A-level maths techniques. From a modern perspective, the limit definition is the meaning of derivative, and it arguably provides us with our understanding of what we ultimately mean when we talk about derivatives of functions. So here, in the extra stuff section to this video, I feel that I don't have to beat around the bush so much, and I can talk a bit more freely about some of the finer points of differentiation that I've maybe had to avoid a bit during the first part of the video. In this part of the video, I'll take a look at some of the history of the concept of derivative and discuss some of the difficulties that mathematicians have had to tangle with when it comes to interpreting derivatives. As always, the contents of this part of the video are not essential for your A-level maths studies, which is not to suggest that there would be no benefit to you having some awareness of some of the things that I'll be talking about. But first, let's have a look at how to geometrically interpret the limit definition and understand the relationship between the gradient of a function at a given point and the gradient of the tangent line drawn at that point. The limit definition of derivative tells us what it means for a function to be differentiable at a point, and differentiable means can be differentiated. If the function is differentiable at every point on its domain, then the function is just said to be differentiable. Let's use the textbook example of f of x equals x squared, the graph of which, of course, looks like the one as shown on the screen now. So now, I'm going to choose 2 points on the curve, namely those corresponding to when x equals 2 and when x equals 4. Draw a line through these 2 points and find the gradient of the line just drawn. The gradient is, of course, f of 4 minus f of 2 over 4 minus 2, which is equal to 16 minus 4 over 4 minus 2, which equals 6. Now I'm going to keep the point corresponding to x equals 2 fixed, but now choose my second point to be the point on the curve which corresponds to x equals 3, Again, draw the line, find the gradient, and it turns out to be equal to 5. Still keeping the point 24 fixed, I choose the second point to be a point a bit closer than previously, draw a line, find the gradient, and keep repeating this process. And what I'll see at each stage is a sequence of numbers corresponding to a sequence of gradients. And this sequence of numbers appears to be getting closer and closer to 4. I'll also see a sequence of lines which seem to look more and more like the tangent line drawn to the graph y equals x squared at the point with coordinates 2, 4. Note that at this stage we do not know what the gradient of the tangent line is. However, no matter how many points I choose, no matter how many lines I draw, and no matter how many gradients I calculate in this way, I will never quite get to 4. Therefore, how do I know that the sequence of numbers is actually going to get closer to 4 and not some number ever so slightly bigger or smaller than 4? I need a more sophisticated approach. So let's stick with the point 2, 4 on our graph, and now choose another point which is some finite distance away from it, but still a point on the graph. The coordinates of this new point will be 2 plus delta x, 2 plus delta x squared. And I can again draw a line through these 2 points and find an expression for the gradient. This expression is 2 plus delta x squared minus 2 squared over 2 plus delta x minus 2, which simplifies to 4 delta x plus delta x squared over delta x, and finally 4 plus delta x. So now as delta x gets smaller and smaller and gets closer to 0, though never becomes equal to 0, there's no question about whether or not 4 plus delta x gets closer to 4. It clearly does. So to capture this idea of delta x being made smaller and smaller, we use the symbol the limit as delta x approaches 0, and write the limit as delta x approaches 0 of 4 plus delta x is equal to 4. And since we saw that the sequence of lines resembles more and more the tangent line drawn at the point 2, 4, then the gradient of that tangent line would seem naturally to have a gradient equal to 4. And that's what we say, that the gradient of the tangent line at 2, 4 is equal to 4. And not only that, we then say that the gradient of the curve at the same point, 2, 4, is equal to the gradient of the tangent line at that point. In other words, the gradient of the curve at 2, 4 is also equal to 4. So now, instead of using the specific point when x equals 2, we could just use a general point with coordinates x, x squared, and go through the whole argument again, but with x instead of 2, and get that the gradient of the curve, and of course the tangent line, at the point with coordinates x, x squared, is equal to 2x. Therefore, the function f of x equals x squared is differentiable at all points on its domain, and the gradient at a given point will be 2x. So more generally, for a function f of x, an expression for the gradient of the line through the points with coordinates x f of x and x plus delta x f of x plus delta x is given by f of x plus delta x minus f of x over delta x. And now to capture the notion of delta x getting closer to 0, and that we are to take the limit of the expression as delta x converges to 0, we write the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, which of course is the limit definition that I gave at the start of the video. There are still some issues with this definition though, and some of these issues I'll mention in what follows in this video, and some of the other issues I won't be touching on at all in this video. So let's have a look now at some of the history of the derivative. The modern limit notion of derivative came about in the 19th century. One of the earliest, if not the earliest formulation of the modern limit definition of derivative is due to Cauchy, who presented what is essentially the same as the definition used today, and which I presented at the start of this video. Here's Cauchy's definition of derivative from his 1829 work, Differential Calculus. The translation from the original French is my own attempt. If the function f of x remains continuous between two given limits of the variable x, and if we assign to that variable a value contained between the two aforementioned limits, an infinitely small increase attributed to this variable will produce an infinitely small increase in the function itself. Thus, if we set delta x equal to I, the two terms of the difference ratio, delta y over delta x equals f of x plus I minus f of x over I, will be infinitely small quantities. But while these two terms simultaneously and indefinitely approach the limit 0, the ratio itself may converge towards another limit, either positive or negative, which will be the ultimate ratio of the infinitely small differences delta y and delta x. This limit, or this ultimate ratio, whenever it exists, has a fixed value for each particular value of x, but it varies with x. The notion of limit, which enters into the definition of derivative, is itself something which needs to be understood in a very clear way before the definition of derivative can really start to make sense, but I won't go into detail here with this because it's a whole other topic in itself. Before this, though, mathematicians worked with infinitesimals. Now, mathematicians working with infinitesimals were often very uncomfortable with them, since even though through using them things seemed to work, at least well enough in many respects, there was a lot of uncertainty about how to interpret these types of quantities, which seemed to be something and nothing at the same time. Nevertheless, mathematicians often put aside the lack of logical foundation for these infinitesimal quantities, since they could apparently be used to solve problems that otherwise wouldn't be possible to solve. There was a big problem for mathematicians trying to understand what infinitesimals were. The notion of infinitesimal was not at all clear, and different mathematicians understood the term infinitesimal in different ways, and even the same mathematician may mean different things at different times during their life. For example, some of the interpretations of infinitesimal, so far as I can see, are, amongst others, that an infinitesimal is a quantity which approaches zero, a quantity which is smaller than any real number but which is not equal to zero, or just zero. There may be other interpretations besides these. The point is that there was no universal agreement on the concept of infinitesimal, with some authors outright rejecting the notion altogether. It's not at all easy to determine in some cases what a particular author means by the term infinitesimal, because in many cases the author didn't seem to really know themselves even what they meant. Before Cauchy, an expression such as dy by dx, and by the way this dy by dx notation is largely due to Leibniz, was understood to be the ratio of two infinitesimal quantities, dy and dx, and so dy by dx was treated effectively like a fraction but with infinitesimals as numerator and denominator, and it seemed that the ratio of two infinitesimal quantities could itself actually be finite, and it was this that was called the derivative. That the ratio of two infinitesimals could be finite is not necessarily as unusual as it may initially sound, but it turned out that infinitesimals are superfluous and can just be ignored, and the modern limit definition of derivative does away with infinitesimals. Whether or not infinitesimals exist is something to which we can, if we wish, remain indifferent, at least in this context. Cauchy's limit definition doesn't suggest that infinitesimals don't exist, but simply that they are not required here. The introduction of the differential calculus changed the nature of mathematics. We read in Maurice Klein's book, Mathematics: A Loss of Certainty, up to about 1500, the concepts of mathematics were immediate idealizations of, or abstractions from, experience. When complex numbers, an extensive algebra employing literal coefficients, and the notions of derivative and integral entered mathematics, the subjects became dominated by concepts derived from the recesses of human minds. In particular, the notion of derivative, or an instantaneous rate of change, though of course it has some intuitive base in the physical phenomenon of velocity, is nevertheless far more an intellectual construct. In other words, mathematicians were contributing concepts rather than abstracting ideas from the real world. As you read more into the history of the differential calculus, other terms that you may encounter are fluxion, evanescent quantity. The Latin verb evanescere means to vanish or to disappear, where fluxion was Isaac Newton's term for what we now call derivative, and evanescent quantities are the dx's and the dy's, the infinitesimal quantities. Isaac Newton, along with Leibniz, are major figures in the history of the differential and integral calculus, with a priority disagreement between them about which one of them was the inventor of the differential and integral calculus, a priority disagreement which is still not completely settled to this day. We also read in Klein regarding Newton. He, Newton, then proceeded to give a new explanation of what he meant by a fluxion. Fluxions are, as near as we please, as the increments of fluents, variables generated in time, equal and as small as possible. And to speak accurately, They are in the prime ratio of nascent increments. Of course, such a vague phraseology didn't help much. And, in his great work, The Mathematical Principles of Natural Philosophy of 1687, Newton made several statements concerning his fluxions. He rejected ultimate indivisible quantities in favour of evanescent divisible quantities, quantities which can be diminished without end. Newton's concept of a fluxion was famously criticised by Bishop George Berkeley in his The Analyst of 1734, where in section 35 he says, "And what are these fluxions? The velocities of evanescent increments? And what are these same evanescent increments? They are neither finite quantities, nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities?" And Klein in his book also talks some about Leibniz. Leibniz's attempts to explain particularly his notion of infinitesimals, infinitely small numbers, are so numerous that many pages can be devoted to them. In an article in The Actor of 1689, he said that infinitesimals are not real but fictitious numbers. However, these fictitious or ideal numbers, he asserted, are governed by the same laws as ordinary numbers. And Klein goes on to say further about Leibniz, the ratio of two infinitesimals he thought of as a quotient of unassignables or indefinitely small quantities, but a ratio which could be expressed in terms of definite quantities. For example, geometrically this ratio of dy to dx is the ratio of ordinate to subtangent. And he, Leibniz, said that the infinitely small is not a simple and absolute zero but a relative zero, that is, an evanescent quantity which yet retains the character of that which is disappearing. However, Leibniz also said at other times that he didn't believe in magnitudes truly infinite or truly infinitesimal. In Bertrand Russell's book, Principles of Mathematics, which is not at all for the faint of heart, we see the following comments regarding the limit definition of derivative. If f of x be a function which is finite and continuous at the point x, then it may happen that the fraction f of x plus delta minus f of x over delta has a definite limit as delta approaches to 0. If this does happen, the limit is denoted by f primed x, and is called the derivative or differential of f of x in the point x. And he then goes on to say, the only point which is important to notice at present is that there is no implication of the infinitesimal in this definition. The number delta is always finite, and in the definition of the limit there is nothing to imply the contrary. In fact, f of x plus delta minus f of x over delta, regarded as a function of delta, is wholly indeterminate when delta equals 0. Russell also says in section 309, the infinitesimal has in general been very vaguely defined. It's been regarded as a number or magnitude which, though not 0, is less than any finite number or magnitude. It's been the dx or dy of the calculus, the time during which a ball thrown vertically upwards is at rest, at the highest point, etc., etc. But none of these notions are at all precise. The dx and dy are nothing at all. Dy by dx is the limit of a fraction whose numerator and denominator are finite, but is not itself a fraction at all. And finally, in section 321 of Russell's Principles of Mathematics, we read, there are in the calculus no such magnitudes as dx and dy. There are finite differences, delta x and delta y, but no view, however elementary, will make x equal to x plus delta x. There are ratios of finite differences, delta y divided by delta x. And in cases where the derivative of y exists, there is one real number to which delta y over delta x can be made to approach as near as we like by diminishing delta x and delta y. This single real number we choose to denote by dy by dx. But it's not a fraction, and dx and dy are nothing but typographical parts of one symbol. Differentiation is a huge topic within mathematics, and so what I've mentioned in this video is a minuscule part of what there is to say about differentiation. Therefore, there will be many gaps in what I've said here, gaps that will be filled in only with a lot of study and a lot of time. Even then, there will always be more gaps to fill, and depending on how far you go into the subject will depend how complicated those gaps will become. Nevertheless, I hope that I've given some idea of what differentiation is about. So this seems like a good place to wrap things up for this video. Thank you for watching right to the end, and I hope that you found this video interesting and useful. Please remember to subscribe to this channel and hit the like button. More A-level maths videos will be appearing on this channel over the coming weeks and months as often as I'm able to make them. If you have any questions about anything that I've mentioned in this video or about mathematics in general, then please feel free to get in touch. See you in the next video. Ciao ciao.